Once again, welcome back to my channel. We have already solved our torque voltage analogy for the same diagram over here, but I'm just going to say that the differential equation for this given mechanical rotational system will be over here, will be same over here for our previous videos. So up to this one, the solution will be identical for both our torque voltage and torque current analogy over here. So I should start from this four different differential equation over there. So I just want to say that just by applying the D'Alembert principle, we have got the first differential equation, which is this one. The second differential will be this one, differential equation will be this one, and the third one will be this one, and the fourth one will be this one. And how do I get that? First, we have converted our much needed conventional diagram into nodal diagram over there, and we have named those number of nodes as our 1, 2, 3, 4. And separately, if you do apply the D'Alembert principle at 1, 2, 3, 4, we have got these four different equations over there. Just do follow our previous videos if you have missed our previous video. To understand for the configuration of this differential equation for these four different equations over there. So right now we have changed our table for our current portion over here, and it is solely focused on our torque current analogy over here. So the parameters will be altered or that is different compared with our torque voltage analogy over here. So I have got the different set of parameters or different set of table over here. Now we do require to put those parameters compare with this mechanical rotational system or mechanical differential equation over there. So just utilize those right hand side parameter for electrical system over here, and just do use that in our given differential equations over there, and let us see what is going to be the equation over here. So we should have started for this four differential equation for our mechanical rotational system over here, and for our torque current analogy, the analogous table is different compared with our torque voltage analogy. I just want to say that the torque is analogous with our current, the moment of inertia that is analogous with our capacitance, the damping coefficient that is analogous with our 1 by r, the spring the rotational spring stiffness that is analogous with a 1 by L, the angular displacement that is analogous with our flux phi, and the angular velocity that is analogous with our voltage E. So here you do feel that the table is quite different over here, and that is been put those parameters in a given differential equation over there. So let us just do start just by configuring our first equation over here. So our first equation is torque. So the torque is analogous with our current I. So I'm just going to write down over here as IT. That is the moment of inertia that is analogous with our capacitance. So this one will be our C1. This one will be D2. The angular displacement that is analogous with our phi, flux linkage phi. So I'm just going to write down over here as phi 1t divided by dt2 for this one, plus k, the stiffness k that is analogous with a 1 by L. So this one will be a 1 by L1, and inside our bracket I do have at this position of our theta 1t or angular displacement, I'm just going to write down over here as flux linkage, which is our phi 1t minus our phi 2t. So this is our first converted, or in a more precise sense, the first electrical equation over here. So just do the same for our next upcoming equations over there. So the next equation will be this one, the equation 2. So the moment of inertia that is interchanged with our capacitance over here. So this one will be C2 D2 phi 2t divided by our dt2, plus the stiffness that is analogous with a 1 by L. So this one will be a 1 by L1, and inside our bracket I do have theta 2t minus of theta 1t, that will be interchanged with our phi 2t minus of our phi 1t, plus once again the k2 will be our 1 by L, so this one will be 1 by L2, and inside our bracket I do have, this one should be our phi 2t minus of our phi 3t, that will be equal to 0. So this is our second electrical equation over here, and I am just going to write down the third electrical equation over here. So let us just do that. So the third electrical equation will be this one, which is quite naturally our, so I should write down over here as C3, this one should be our D2, at the place of our theta 3 I am just going to write down over there at the as the flux, so this one should be our phi 3t divided by our dt2 for this one, plus k2, the k2 is our 1 by L2, so this one will be our 1 by L2, and inside our bracket I do have phi 3t minus of our phi 2t for this one, plus b3 is 1 by r3 dt of phi 3t means our dt of phi 3t for our third equation over there, and the last part will be plus our k3. The k3 is our 1 by L3, so this one should be 1 by L3, and inside our bracket I do have phi 3t minus of our phi 4t, that will be equal to 0. So this is our third electrical equation over here, and let us just go for that fourth electrical equation, which is this one. Okay, so the torque is analogous with our current, that is it. The moment of inertia, that is analogous with our capacitance, so C1 d2 phi 1t divided by dt2 plus 1 by k1, that is analogous with 1 by L, so this one will be 1 by L1, and inside our bracket I do have phi 1t minus of phi 2t, and for that second equation we do have the moment of inertia, that is analogous with the capacitance C2, so this is C2 d2 phi 2t divided by dt2 plus of k1 is 1 by L1, this one should be a phi 2t minus of phi 1t plus 1 by L2, this one should be our phi 2t minus of phi 3t, which is equal to 0. And for that next equation, the third equation I have written over here, you can see that the moment of inertia, that is analogous with our capacitance. So this one would be a C3 D2 phi 3t divided by D32 plus K2 is analogous with the 1 by L2, and inside our bracket I do have phi 3t minus of phi 2t plus of B3 means our 1 by R3, because damping coefficient, that is analogous with our 1 by R, so this one will be our 1 by R3 ddt of our phi 3t, and for that last term we do have plus 1 by L3, this one should be our phi 3t minus of phi 4t, which is equal to 0. So this is our third electrical equation, and let us just go for that last equation, sorry for that one. Okay, so for the last equation we do have this fourth equation over here. So as we have already converted that mechanical rotational equation into electrical one over here, so I am just going to erase these first three equations over there, and let us just do convert the fourth equation over here as well. So for that fourth equation, once again, if you do follow the same procedure over there, the J4 D2 for theta 4t divided by dt2, the J4 is the moment of inertia, that is quite naturally the C4. This one should be our D2 540 divided by our dt2 for this one, plus b4 is our 1 by r4, and this one should be our dt of our 540 plus or k3, that is analogous with our 1 by l. So this one should be our 1 by l3, and inside our bracket I do have 540 minus about 53t, that will be equal to 0. So this is our fourth electrical equation over here. So just by looking at this table, we have converted our mechanical differential equation into electrical one over here, but still we can see that these equations do require further modification, to say the least, or to have the final diagram for electrical systems over there. I hope you have totally understood up to this one. If you still have any doubts, please let us know in the comment section for better understanding. Do like, do share our videos, and keep following our channel. Just wait for my next part.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.